Hi, my name is Dr. Ruth Walker, and I am going to talk you through a two-way ANOVA. This video is going to talk about what we use two-way ANOVAs for, what are the hypotheses associated with this particular type of statistical test, what assumptions do we need to check our data for if we're going to run a two-way ANOVA, as well as how do we run and interpret a two-way ANOVA. If you're interested in the math behind a two-way ANOVA, that is not something that this video is going to talk about. So let's start off with, what do we even use this for? A one-way ANOVA is looking at and comparing three or more different groups. It's really an extension of an independent samples t-test, right? So an independent samples t-test is comparing the means of these two independent groups, and then we get a one-way ANOVA. We have a little bit more flexibility. We can look at three or more groups. With a two-way ANOVA, it is even more of an extension of that one-way ANOVA in that we can do two factors or two independent variables at the same time. And why we're doing that is because we think that there's an interaction between those two factors on whatever our outcome or dependent variable is. So essentially what it is saying when we're looking at an interaction effect is that the impact of our first factor depends on our second factor in terms of how is it impacting that outcome variable. On the right-hand side, you can see the example that I set up for us to look at today. And this is just a quick example, and then I'm going to walk you through data and an example where I have actual data for us to walk through. So for this one, what I thought would be interesting to know is there differences in student performance depending on the way that their course is being presented? So right now, we're in the middle of a global pandemic, so a lot of universities and schools have had to change up the modalities and the formats that they're presenting their coursework in, particularly when we had a lot of lockdowns happening throughout the United States and beyond. So we were no longer able to do in-person classes, so some professors moved to synchronous online classes, so holding their class at the same day, same time, and just holding it in some virtual format such as Zoom. And then we also have asynchronous online classes, which are typical and commonly used by students who are online students and in online programs. So this is where students are completing their coursework when it's convenient to them and at the timing of their choosing. So our second factor that I have here is year in school. So senior, junior, sophomore, or freshman. So what I'm interested in asking is, does student performance depend or is it impacted by the way that their course is being presented? And is it also impacted by the year they are in school? So are our freshmen struggling more because of the different presentation formats and also being new to school? And are our seniors doing better because they have more experience and coping skills and study skills and things like that? Also, they're more likely to be taking classes that are in their major and in their interest area, versus freshmen are more likely to be in, general education courses that they may not enjoy. So do we see differences that way, or is it completely opposite? Are seniors struggling because they are used to always having in-person classes and freshmen aren't because they're new to the university anyways? So a two-way ANOVA is great for this type of research question because we have these two factors that we think might impact student performance, and we think that they might interact in this really unique way, and that would allow us to test that kind of question out. What would our null hypotheses be if we ran this particular type of statistical test here? So we have three hypotheses with the two-way ANOVA. Our first hypothesis is dealing with our first factor. And what it is doing is, we call this a main effect. We're looking to see, is there a main effect for our first factor? In this case, our first factor is going to be course presentation format. So our null hypothesis for our first factor would be, there is no difference in student performance between the three types of course presentation formats. This hypothesis is the same type of hypothesis you would write when you're working with a one-way ANOVA. Hypothesis 2 is going to address our second factor. It's going to look to see, is there a main effect for that same second factor? So our null hypothesis here would be there's no difference in student performance between freshmen, sophomore, juniors, and seniors. Again, another hypothesis that looks like a one-way ANOVA hypothesis. Our third hypothesis is where it varies, because again, we're doing this two-way ANOVA because we're interested in the interaction between those two factors. So this null hypothesis says there is no interaction between course presentation format and year in school on student performance. We are interested in both of those variables. Understanding an interaction effect requires that we look at a couple different things. So you can see here, if we're looking at all of the different groups that we're going to have with the different levels of these independent variables or factors, there's 12 different groups. This is where it gets to be really complicated. It's why I stay very far away from any math related to this type of analyses. So we have two factors: course presentation format, year in school. And the next question is, how many levels do we have in each of those? And in the statistical notation, we signify that with a K. So K equals what? So if we're looking at course presentation format, we have 3 different levels. K will equal 3. In-person, synchronous online, asynchronous online. Our second factor is student year in school. We have 4 levels, or K will equal 4. Freshman, sophomore, junior, and senior. When we put both of those together and make this table of, that is 12 different groups that we're going to be comparing the means across to see, is there a difference? Is there a meaningful or statistical difference in student performance depending on both of these factors? So I don't have that data. So what I do have data for is another type of two-factor ANOVA that I ran with some colleagues of mine. We were interested in predicting bystander behavior or helping behavior in sexual harassment scenarios. And so I'm going to talk you through some of the results of that publication and use it as an example for going through and interpreting and analyzing data. If you want to learn more about that, the data that we're working with, and more about the different results and things that we had, I would refer you to that paper. It's called Cornered at a Bar: How Victim Clothing, Alcohol Intake, and Relationship with Bystander Impact Intention to Help. It's not a mouthful or anything. Okay, so predicting bystander behavior. What is bystander behavior? So bystander behavior is how likely is someone who is witnessing something happening, and in the case of this paper, or what we're interested in is how likely is it that someone witnessing a sexual harassment happening would be to intervene and do something about it. Most often, bystanders who see something happening don't do anything about it. They are passive bystanders who don't get involved. So our research is really looking at, how do we get people empowered to do something? What impacts that? What impacts how likely someone is to stand up and say something or intervene or do something about that? So in our particular study, participants read a scenario where they were reading about a woman in a bar who was being harassed by another man in the bar. And we manipulated a couple factors to see if that impacted how likely they would be to intervene. So one of those factors is relationship with the victim. That is something in the research that we know impacts bystander behavior. So the past research has found that when a bystander knows the victim, if they're a friend and they know them, they're a lot more likely to intervene than if it's a stranger, someone they don't know. What we also know is that level of intoxication of the victim matters, and we knew that in this case from a previous study my colleagues and I ran. So this particular paper looked at 2 different studies at the same time. So what we knew is that, interestingly enough, people were more likely to intervene if the victim had been drinking than if the victim was sober. So with relationship with the victim, we wanted to look at a couple different levels. As I mentioned before, previous research has compared strangers and friends. we wanted to know, what if we add acquaintances in there? What if we add all of these people, like our neighbors, our classmates, people who we wouldn't consider a friend, but we also wouldn't consider them a stranger? So we wanted to know, does that impact bystander behavior as well? So with our first factor, relationship with victim, we had 3 levels: stranger, acquaintance, and friend. And with our second factor, victim alcohol intake, we had 2 levels. We had sober and drunk. And so for relationship with victim, K would equal 3, and for levels of victim alcohol intake, K would equal 2. And what we really ran, the very specific name of that design would be a 2x3 factorial ANOVA. And you can see that matches how the cells in that table kind of match up. It's a 2x3 design. What are our null hypotheses? So again, we have 3 hypotheses here. Hypothesis 1, bystander behavior does not vary by level of victim intoxication. That's our first factor. Hypothesis 2 is related to our second factor. Bystander behavior does not vary by relationship status with the victim. Hypothesis 3, this is our interaction term. There is no interaction between relationship status and level of intoxication on bystander behavior. We also have to, before we run any analyses, check assumptions. So when we're running a two-way ANOVA, there are 6 different types of assumptions we want to look at. We want to make sure our DV is continuous, our IVs are categorical, we have independent observations, no significant outliers, that each group's data are normally distributed, and that we have homogeneity of variances. So let me talk you through each of these. First one, assumption that we have a continuous dependent variable. For our dependent variable to be continuous, it needed to have been measured at the interval or the ratio level, and we measured it at the interval level. So it was a Likert scale that participants answered questions on, and it had 3 subscales. So we looked at 3 different types of bystander behavior. So distract, delegate, and direct. So distract is when you're causing some sort of distraction. An example would be, I would try to distract the person in the scenario by asking her if she knows where the bathroom is. Delegate would be something like, I would ask my server if they could check on the woman in the scenario and make sure she was okay. And then the last type is direct. I would approach the woman in the scenario and ask if she wants the man to leave her alone. So by adding up all of these different items and the ratings of, I would be very likely to do this versus I would not do that at all, it gives us a nice interval level variable, so we meet this assumption. Our next one is that we have categorical IVs. So this means that both of our factors are measured at the nominal or ordinal level. So relationship with victim, stranger, acquaintance, friend, that is going to be a categorical variable. And victim alcohol intake, drunk versus sober, again, another nominal level variable. Assumption 3 is that we have independent observations. So this means that people who are in our first group who read the scenario about the woman who was a stranger to them and was sober were not also in any other group. So if they read that scenario, they didn't also, for example, read the sober friend scenario or the drunk acquaintance scenario. Each person needs to be isolated in their own group and not have been exposed to any other groups to meet this assumption. And we did have this. All the participants were randomly assigned to one of these 6 groups, and they did not read any additional scenarios. Fourth assumption is that we have no significant outliers. So to do this, we look at a box plot. It's one of the easier ways to do it, although there are other ways and methods of looking for outliers. It's just simpler. So for doing this in JASP, I have the instructions up there on the slide for how to do it. You're going to go up to descriptives, choose descriptive analysis. You want to put your dependent variable in the variables box and put your factors in the split box. So you'll start with your first factor, IV1, and then you'll go to your second factor, IV2, and do both of them so you can get what we have on the right side, that output. So what you want to do is go to plots and click box plots. I like to click for them to label the outliers so I know what participants it is that were considered outliers. I also like to click on jitter element, which plots all of the data points there in that sample. So when you're looking over to the right, you can see that we do have some outliers here. We have some, if you look at the high alcohol intake, you can see participant number 187 up there. Definitely an outlier, 163 down below it. You can see some outliers, a couple in the acquaintance condition down below and the friend condition. When we're doing a two-way ANOVA, it is fairly robust to some violations of this assumption. What I do as a researcher is when I have outliers, it's very much a subjective decision, but there are a couple things that I do first. So I go to each of those participant numbers and I make sure there isn't some data entry error. I also make sure that the participants weren't randomly responding, that they didn't just choose like all strongly agree, for example, that it is real data. That's the first thing. And also that they didn't finish a scale that should have taken 30 minutes in 2 minutes. So that would also be a big indicator for me that maybe that data is not real as well. So those are the first things that I try and kind of rule out when I'm trying to decide, am I going to keep this person in or not. Another thing that I oftentimes do, and I did with this particular set of data, is I ran the analyses with the outliers and without the outliers, and I wanted to see, was there any difference? There was not. The results were exactly the same. So for me, I kept them in, and that is a preference that I try to have when I am running analyses. But again, you might be working with an advisor or have an instructor or someone who wants something different. Fifth assumption is that our data are normally distributed. For this, again, there are some variations in terms of what people prefer to look at. I prefer to look at the skewness and kurtosis statistics. Ideally, you want those statistics to be between -1 and +1, although people don't agree on what those numbers should be. So some people will say -0.5 and +0.5. Some will say -2 and +2. Or -1.5 and +0.15, 1.5. So there is a lot of variability in terms of what people think those statistics should be to be acceptable. So you might want to look and check with your people in your discipline to see if that's what they prefer, or with your advisor, or with your committee, or whoever it is that you're working with. For myself, I try to stick with one. If you're getting closer to 2 or more, then you might need to do a log transformation to make that data look more normal before you run these analyses. To run these analyses in JASP, pretty easy. When you're already in descriptives, you can just go down to the statistics tab, click on that. You're going to click on skewness and kurtosis. You can also click on the Shapiro-Wilk test, which is another option right underneath them. And what that test does is it is a normality test. The issue with that test is that it's pretty sensitive to sample size. So the bigger our sample size, the more statistical power we have, the more likely we are to have a p-value that's significant and reject that null hypothesis that we always want. So when we're checking hypotheses, generally we want to have a significant p-value. When we're checking assumptions, we don't want a significant p-value. So having an assumption check that is sensitive to sample size and that kind of power is not always a good thing. And so I prefer to rely on skewness and kurtosis statistics instead, because when we have a large sample size, that Shapiro-Wilk test is not always as accurate. So if you look over on the left-hand side, you'll see one example of these statistics. If we look at our skewness statistics, you can see it's -0.59, and our kurtosis statistic is 0.72. So those are both within that range of -1 to +1, so I am happy with them. If you look down at the Shapiro-Wilk test, look at the p-value for the Shapiro-Wilk, you can see it is 0.007. So it is significant. It is less than 0.05, and that means that according to that test, our data are not normally distributed. But again, I don't like to rely on that test because it's sensitive to sample size and is not always as accurate. So I prefer to rely on the skewness and kurtosis statistics. Last assumption is homogeneity of variances. It's, do we have equal variances between these groups? To test this assumption, you're going to look at the Levene's test. And again, like I just mentioned, you don't want this test to be significant. Because it's a test of assumptions, you want that p-value to be greater than 0.05 so you can say, I'm meeting this assumption. This is the results of our Levene's test for this particular set of data. And you can see our p-value is 0.056. So we're happy with that. It's right on the border. Had it been any lower, it would have been significant and we would not have met this assumption. But very fortunately for us, it was greater than 0.05 just. And so 0.056, we're happy with that. We're meeting that assumption, so we're able to move forward with running these analyses. When we're determining whether or not we're going to reject our null hypotheses or fail to reject our null hypotheses, we have three things that we really need to look at for our omnibus test. So the omnibus test is looking at each one of those hypotheses, looking at our first factor, our second factor, and our interaction. So we have to look at an F statistic for each of those. So we have an F statistic to look at for factor 1, we have an F statistic to look at for factor 2, and an F statistic to look at for an interaction term. So we have 3 hypotheses, 3 Fs, and 3 p-values that we're going to look at and interpret for this particular test. When you're conducting this analysis in JASP, these are just the instructions. You're going to go up to that ANOVA box, go down to the first ANOVA and choose it. You want to put your dependent variable in the aptly named dependent variable box. You want to put your IVs in the fixed factors box. You're going to click on a couple different things underneath there. You want to click on display and then estimates of effect sizes. There are multiple types of effect sizes here. They're all saying very similar things, so you have your choice. And I'll talk a little bit more about those later on. Also, for assumption checks, you want to click on homogeneity test there. This is where we get that Levene's test that we just looked at. Under post-hoc tests, you're going to move your IV1, IV2, and your interaction terms over to the box on the right. And you want to check 2 key tests. Those are the post-hoc tests we're going to look at first, confidence intervals. And I asked JASP to flag significant comparisons only because I'm lazy and it makes my job a lot easier when I go to interpret. So making a decision. These are our omnibus test results over here to the left for our 2-factor ANOVA. You can see we have 3 F statistics and 3 p-values to interpret, and each one of those goes with one of our hypotheses. So for IV1, we have to, our first factor, we have to look at that F statistic, we have to look at another one for our second factor, and another one for the interaction term. Let's focus on the first IV, our first factor. If we look at the p-value with that, you can see our p-value is 0.155. So what do you do with that? How do you decide? If the p-value is less than your alpha level, which in psychology it's generally 0.05, you're going to reject your null hypothesis. If your p-value is larger than your alpha level, which again is 0.05 in this case, then you're going to fail to reject your null hypothesis. In this case, our p-value of 0.155 is definitely larger than 0.05, so we are going to fail to reject our first hypothesis. Our first hypothesis, as a reminder, is bystander behavior does not vary by level of victim intoxication. So what that F statistic just said is that it doesn't vary there. So we don't have a main effect for level of victim intoxication. And in terms of making that decision again, if P is greater than 0.05, we're going to fail to reject that hypothesis. Looking at our second factor, looking at that p-value, you can see it's 0.029. So that is less than our alpha level of 0.05, so that is significant. So because our p is less than 0.05, our decision for the second hypothesis has to be to reject our second null hypothesis. And again, that null hypothesis was bystander behavior does not vary by relationship status with the victim. So we are rejecting this null hypothesis. There is a main effect for relationship status. There's some difference there. Going to our third F statistic, so we're looking at it for our interaction term now. Looking at that P value, you can see 0.020. Again, this is less than our alpha level of 0.05, so this is significant, which means that when we're looking at hypothesis 3, P is less than 0.05, so we're going to make the decision to reject our third null hypothesis. And that null hypothesis was there is no interaction between relationship status and level of intoxication on bystander behavior. So this is saying that there is a significant interaction. Something is happening here. And there is some disagreement in terms of when you have a significant interaction, should you even interpret the main effects? So there is a little bit of disagreement in terms of whether or not you should. So some people say if you have a significant interaction, you should not even interpret the main effects. Other people say you only interpret, and you would say that you only interpret the main effects if the interaction term is not significant. So you can see some variations in terms of people's preferences there. Effect size test. I said I would come back to this. So in JASP, there are 3 that you can easily click on. So the eta squared, partial eta squared, omega squared, and you can see that those effect sizes are up there. So what they're really saying is how much of the pie are you predicting in your outcome variable? In this case, we're trying to predict bystander behavior. So that's our pie, and those effect sizes are telling us how much of that pie are we predicting. They're all very similar, and in terms of which one should you use, it depends on sometimes the discipline, sometimes it depends on the advisor, your instructor, the journal you're trying to publish in. So in terms of which one should you report, it doesn't matter a whole lot really. So pick the one that you like the best, I would say, because they're saying very similar things. We are not done. So we have decided what we need to do with our null hypotheses. We've looked at those Omnibus F-test results, but we don't know what it means. We have no idea what it means. There's an interaction, but why does that matter? What is the real world meaning behind that? So we have to do some more work. So looking at the main effect for a first factor, and again, some people would say you should not be interpreting main effects if you have a significant interaction. So take these results and this with that in mind. So how do you look at main effects in JASP? You're going to go to Post-Hoc Tests. You'll move whatever factor it is that you're interested in to the box on the right. You want to check Tukey, confidence intervals, and I also asked JASP to flag significant comparisons. So if we remember from our Omnibus test, we didn't have a main effect for level of intoxication. It was not significant. So if we didn't have that significant at that level, we're not going to look at post-hoc tests. Like across the board, we can agree that. And just doing this for practice for you to look at it, you can see that it agrees with that Omnibus test. The p-value for this Tukey post-hoc test is 0.155. It's saying there's no difference. I already told you there was no difference. So there's no difference between the low alcohol intake and the high alcohol intake on bystander behavior. So let's go to our second one. So our main effect for our second factor. So again, the instructions for what to click on in JASP are there on the screen. They're the same as the last one. Let's look at our p-values here. When we're comparing stranger to acquaintance, we have 0.997. There is no significant difference. That is greater than 0.05. When we're comparing stranger to friend, we have 0.049, so it is just significant, and it just made it. And you can see that JASP flagged that comparison for us. They put a little star beside it to tell us, hey dummy, this is significant, in case you didn't know. And then that last one is comparing acquaintance and friend. So 0.060, it's not flagged. It's so close to being under 0.05, but it is not. So it is not significant. So when we're looking at what is driving this main effect here, we can see it's really being driven by the differences in bystander behavior between the stranger condition and the friend condition. The interaction. So now we've looked at the main effects. Now we have to talk about this interaction term. How do we interpret this? And it is difficult to interpret, and people, again, do it in different ways. So I'm just going to talk you through one way, and the way that I preferred to do it, and the way that I did it in the paper. So for this, I like to look at a plot of the data. It helps make it so much easier for me to understand conceptually what's happening if I can see what the data looks like visually. So I go to descriptive plots, and I move your might want to play around with it depending on what you're looking at, but I move the IVs to either the horizontal axis in the separate lines boxes. You can also ask JASP to display different types of different boxes and plots. So I recommend playing around with it and trying different ways of viewing the data until you get what makes the most sense for you conceptually for you to be able to interpret it. One of the things that I do always check when I'm there is I check display error bars, because that lets me see not only the mean plotted on there, but the variability within each of those variables. So when we're looking at this here, we can see with the white dots that are going across, that is for the low alcohol condition. The filled in dark black dots are for the high alcohol condition. And this shows you where we can see differences. And the reason for the error bars is that when you see error bars that aren't overlapped or aren't overlapped very much, that's oftentimes where we're going to see our significant comparisons and our significant differences between those groups. So for example, let's look at that acquaintance group right there. You can see for the low alcohol condition, levels of reported bystander behavior are lower than in the high alcohol condition where that mean is a lot higher there. So we don't know if it's significant yet. We have to look at our post-hoc tests, but just looking there and seeing how little overlap there is between those error bars makes me think that there might be a difference there. There might be a significant difference when we're looking at these different post-hoc tests. So simple main effects is one of the ways that people oftentimes interpret a two-way ANOVA, and that's the way that I'm going to talk about here. So what a simple main effect is really doing is it's looking at the simple main effect of, for example, in this case, alcohol level, so low alcohol versus high alcohol at each level of relationship type or relationship status. So to do a simple main effect, you go to the simple main effects little section in JASP. It's nice and labeled, nice and easy to find rather. You're gonna move your IV2 into the simple factor, and then you're gonna move IV1 to the moderator factor, and that'll give you your output, and you'll switch it up and do it both ways. So here we can see our p-values are both significant, 0.026 and 0.021. So that is telling us, and what it's really comparing is it's seeing, is there differences in this? So what I did is ask JASP to make me other plots, and I have a plot for, on the left, for a low alcohol intake, the different levels for low alcohol intake at the stranger level, acquaintance level, and friend level, and that was significant. So there is a significant difference between those three groups there. And then also at the high alcohol intake, we have stranger, acquaintance, and friend, and that was also significant. So what it tells us is there's a significant difference between those three groups there. So if you're looking at those three groups, and again, you're looking at those error bars, what you would suspect is in the low alcohol condition, we have a significant difference there between stranger and friend, because those are the two error bars that aren't overlapping. And then in the high alcohol condition, the group that's on the right there, you can see there's not a lot of overlap happening between acquaintance and friend in that high alcohol condition. So that simple main effect test tells us that there's a difference in these groups, and then looking at these and interpreting those error bars can help us see where that difference really is. So let's look at it now looking at the simple main effect of relationship status at each level of alcohol. So you can see here in the stranger condition, our p-value is higher at 0.26, that's not significant. In the acquaintance condition, our p-value is 0.005, so that's significant. It's significantly less than our alpha level, 0.05. And then the friend condition, our p-value is 0.47, so again, greater than 0.05, not significant. So visually, this is what we're talking about. So in the stranger condition, there's not a significant difference in bystander behavior between the low alcohol and the high alcohol levels. In the acquaintance condition, there is a significant difference in the levels of bystander behavior between low alcohol and high alcohol. And that is, remember when we were looking at the overall interaction, that's what I said I would suspect is happening based on the error bars and what that looked like. And then in the friend condition, there is not a significant difference between bystander behavior in the low alcohol condition and the high alcohol condition. So for simple main effects, it gives us the level of one factor at the levels of another factor. So again, this is our overall interaction. This is what it looks like. This is what we started off with. And those simple main effects are really telling us what it looked like when I first looked at it, is that what is driving this interaction really is that difference that's happening at the acquaintance level. So if the person in the scenario was drunk, had drank a high level of alcohol, and we described her as like falling off the stool, for example, the participants were significantly more likely to say that they would help her than if the acquaintance was sober. And that is actually, if you look across all the different conditions and everything, people were more likely to help a drunk acquaintance than they were anyone else, which is not what we expected. We expected people to be more likely to help a friend, which is what previous research has shown, but previous research has not looked at acquaintances before. And so throwing that in there was something new, and it showed us that really there are differences if we are teasing out not only do you know somebody, but how well do you know somebody? So maybe if we have a friend and we are less likely to help them compared to acquaintance because maybe we know them better, maybe we know what they would prefer, maybe we know their preferences and what they can handle, or what we think they can handle anyways. Versus an acquaintance, there's more ambiguity there, but there's also still that tie of maybe a responsibility because we know them and we want to protect them in some way. Versus a stranger, there is also very ambiguity there, which is oftentimes why in past research we see people less likely to intervene and do something if it's a stranger, because sometimes they feel like it's not their business, it's not their place. So there are the results of our study, and I'm walking you through and how do you interpret it, how do you look at that, how do you analyze it in JASP. And our results are not what we expected, and sometimes that happens in research, and you have to try to figure out, well, what could happen? And then you have to run more tests and more studies to kind of tease that out, and why did we have that result? Why did we get that? So in closing, if for those of you who found this study interesting, and those of you who didn't, I would still suggest that bystander behavior and bystander interventions to prevent sexual assault and sexual harassment are super important, and they've been shown to work. So if you see something, take responsibility, say something, do something. And I would recommend looking into different types of programs that you can take to learn more about this area of research. So for all of you who've made it this far, thank you so much. And if you have questions, you're always welcome to put those questions down in comments, and if I can respond to them, I'd be happy to.